Hello everyone, my name is Qi Yan from Shanghai Jiao Tong University. This video presents our paper on a novel measurement scheduling technique for cooperative localization. In cooperative localization, mobile robots improve their localization accuracy by jointly processing the relative measurements they take with respect to each other. This is of interest in operations where access to GNSS signals and external landmarks are challenging. For example, in underwater operations or in indoor localization for uncharted maps. In practice, the robotic systems need to take care of a lot of things and only a portion of their resources are allocated to localization. For cooperative localization, to process every inter-agent relative measurement, the robots need to communicate with each other and do processing locally, which will lead to large communication and computation costs in some cases. Simply put, the more relative measurements the robots take, the better the accuracy is, but the costlier the algorithm becomes. Therefore, this constitutes the focus of this work: how to reasonably reduce the communication and computation costs by smart management of inter-robot relative measurements. To solve this problem, one of the popular approaches is to determine the optimal measurement frequency given the resource constraints. These methods usually assume a fixed sensing topology throughout the operation and use covariance upper bound analysis to determine the relative measurement frequency in the team. They are generally based on the discrete time or continuous time algebraic Riccati equation. The convergence of the Riccati recursion requires that the overall system has full observability, which means there must be at least one robot accessing absolute positioning information, such as GPS signals. The observability requirement is, however, a very hard constraint and cannot be satisfied in many conditions, which limits the use of such algorithms. Moreover, these methods usually rely on exhaustive search, which may not be a practical choice for real-time implementation. Another approach for cost management in cooperative localization is via measurement scheduling, in which robots get restricted to take only a certain number of relative measurements, but they have to choose their landmark robots in a way that the positioning uncertainty is minimized. There are a couple of previous work about measurement scheduling, and the uncertainty measure that is minimized is mainly the logarithm of the determinant of the joint covariance matrix, or its trace. It is known that the optimal measurement scheduling, like the sensor selection problem, is NP-hard. Therefore, the main effort is on proposing suboptimal solutions with reasonable computational complexity. The submodular function has a diminishing marginal gain. The previous work mainly made use of the submodular property of the log determinant to propose suboptimal greedy solutions, which come with non-optimality gap. These methods, however, induce high inter-robot communication cost in scheduling process. They all require real-time robust state estimations of the whole team in order to do scheduling for one robot. So the aim of our approach is to cope with the aforementioned challenges in terms of communication overhead, computational cost, and observability requirements. We use the log determinant of the joint covariance matrix as our uncertainty measure, and we want to minimize this objective by choosing relative measurements locally. For each robot I, the goal is to choose its landmark robots smartly given the constraint on the number of relative measurements. Based on the dynamic model for robots moving on a flat surface, the upper bound of the objective is constructed, and its denominator includes a key term that reflects the correlation level between the state estimation of the master and the landmark robots. In a straightforward way, we carry out the optimization by lowering the upper bound. For each robot I, there are a certain number of landmark robots in its detection zone, and each of them corresponds to a unique Jij term. By ranking all the Jij and selecting the largest Qi once, we could easily get an approximate solution to the scheduling problem. To sum up, the scheduling and localization work together as follows. Firstly, the master robots detect the potential landmark robots in its measurement zone. Then each master robot locally computes and ranks the Jij terms in order to select its best measurements. Afterwards, the cooperative localization continues and does the rest of the work. During the scheduling process, all the terms in the covariance upper bound are locally stored at each master robot, and therefore the algorithm doesn't require any inter-robot communication to do computation. That is, there is no need for the robots to collaborate to carry out the landmark robot selections. Also, it can be carried with reasonable computational complexity in real time. Each time complexity is only n log n, where n is the number of robots. Moreover, the solution does not assume full observability and could be carried out in operations with only relative measurements. So now we demonstrate the efficacy of our scheduling algorithm by comparing its performance to reference 19 and the random selection in two sets of simulation studies. In the first study, the UTS dataset is used, in which a team of 5 robots move on a 2D flat surface in an indoor environment. In the figure, the thinner line corresponds to Qi equal to 1 and the thicker one to Qi equal to 3. This plot shows that if robots process all the feasible relative measurements, the best localization accuracy is achieved. However, as expected, when the robots are restricted to take Qi number of measurements, the performance drops. This is a trade-off for lower communication and computation cost. Our method uses a comparable performance to the solution of 19 for both cases of Qi equal to 1 and Qi equal to 3. However, we recall that our algorithm does not require any inter-robot communication at scheduling stage, as opposed to the method of 19, which requires all-to-all communication. The figure also shows that the random selection delivers an inferior performance, especially in the case of Qi equal to 1. So it's even more important to solve the optimization problem when there is a limited number of resources for measurements. Next, we demonstrate the effectiveness of our method through a Monte Carlo simulation study for 9 robots. This figure shows the time history of the logarithm of average determinant from m equal to 50 Monte Carlo simulations. Clearly, we can observe the same trends as before when we do the comparisons between these methods. This figure shows the average, the RMSE result for the Monte Carlo study. Although it is not included in the optimization objective, it is of interest for many practical applications that the cooperative localization significantly outperforms the dead reckoning-only localization and the random selection as well, particularly in the case of Qi equal to 1, where the available resources are very limited. This table shows the average execution time of the algorithm in 19 hours from our Monte Carlo simulations. The proposed method is substantially more efficient than the algorithm of 19 and also has better scalability with respect to Qi and n. In this paper, we study the problem of lowering the communication and computation costs of a 2D cooperative localization algorithm by relative measurement scheduling. We provide a new method that allows each robot to choose its restricted number of landmark robots locally without any collaboration with other team members. Our solution does not require full observability and has a polynomial time complexity. As a result, the proposed algorithm can be a practical solution for real-time implementation for robotic teams with resource-constrained robots. Our future work includes extending our results to landmark selection for loosely coupled cooperative localization algorithms, where the cross-covariance terms are not maintained but accounted for implicitly. Thanks for your attention.